How are we doing today? Doing all right? Okay, so the plan for today is to continue talking about material in chapter 14. Last time we introduced functions of several variables, spent some time talking about surfaces, introducing some ideas, and what we want to focus on now is transitioning to being able to discuss calculus and what that looks like in this new environment. Okay. Now, in order for us to be able to talk about calculus, we have to talk about limits because the infinite processes that allow us to perform the operations of taking a derivative or computing an integral require that we have access to infinite processes, which mathematically we represent through limits. And unfortunately, there are a little bit of complications that come up when we look at how these things go together. So let's start off with a couple of examples of functions of two variables. So here first we have f. In the numerator we have sine of x squared plus y squared, and in the denominator we have x squared plus y squared. And then for our second function, we have in the numerator x squared minus y squared, and in the denominator the same thing as the other example, x squared plus y squared. So what we can do is we can create tables of values for these things by plugging in a bunch of numbers. In the context of writing that out on a piece of paper, not the easiest thing to do. We could ask a computer program to do it for us or something, and get a list of values. For us, it's going to be easier if we just probably look at the graphs of these things. So we'll start there. It gets really wild until we get the stuff put together here. Okay, now we can see that the way that this looks is it has this kind of this ripple effect to it. And near zero, it has this sort of constructive interference hump that it gets where the value looks like it's doing something that's probably okay. All right, now we're interested in limits and continuity, as I said, title of the section. And looking at this picture here, without doing any hard work, we can see that this surface is probably fine, right? Based on the equation over here, the value that we would definitely be worried about would be what happens at zero, right? That's the troublesome point. When x squared and y squared both get close to zero, that is, we're looking at the point here on the xy plane. The part of the surface that's directly above that or below, it would be negative, would be where the trouble could occur. We don't seem to have any trouble here. If we type in our other example, things look less nice. Okay, we need to pay very careful attention to what's going on with our different axes here. Okay, this part here is the axis where y is equal to 0. Okay, and we see that we're up here at positive 1. See, there's almost a straight line here, right? And if we turn this and look at instead the place where we have x equal to 0, so we're on the y-axis, we see that we're down here at negative 1. Okay, this is a big problem if we get close to 0, because depending on what direction we're coming from, I don't get the same answer. In this example, every direction that I head along the surface towards 0 gives me, or so the point 0, 0 gives me the same limit. Okay. In this example, it depends on what path I take. That's a problem. Okay. What it means is that the surface is not continuous here. Okay, so there's a continuity problem at 0 because I can take multiple paths and get different answers. So in the left case, we can say that the limit as xy approaches 0, 0 of f of xy is equal to 1. And here, the limit as xy approaches 0, 0 of g of xy does not exist. Yes. Okay, so to answer the question, overall, when we are dealing with functions of several variables and talking about limits, we're going to have to be more careful. Okay, what you just described, which is, say, plugging in the value 0, 0 into both of these equations, is something that you're only allowed to do when the surface is continuous. Okay, the rules for that were the same when we were dealing with one-dimensional functions. You're only allowed to plug in the point if you know that the function's continuous. So in the cases of polynomials or things like that. All right, we're going to inherit some of those properties where if the surface is continuous, then we can just evaluate it at the particular value. But we learned that this surface is not continuous. Okay. If I plug in 0, 0 here, yes, I'm going to get something that looks like sine of 0 over 0, but there's a reason why that limit exists. Okay. And over here, there's a reason why it doesn't. We'll explore that here. Yeah, it takes a little bit more work, is the best explanation I can give until we start getting into some more details here. All right. But the problem is this. Okay, we have one case where it works, another case where it doesn't. In terms of complexity, these things don't look like they're too different, but there's an issue here. Okay, in both cases, as we just mentioned, we get something that basically looks like 0 divided by 0 if we naively plug in the values, but that doesn't mean that we're going to get limits that make sense in either case. All right. Now, the rule is this. Sorry. So in order for us to have a limit that exists, it is necessary for every path along the surface to result in the same value. Okay, this was the issue that we had in the examples that I showed before. Every way that I could go towards 0 in the bumpy example was fine, but in the split sheet, if I came along the y-axis, I got a different answer than if I came along the x-axis. And that disagreement resulted in a limit that doesn't exist. This is just like the cases we had in Calc 1, where the limit at that point does not exist because I get different answers if I come from different directions. The limit from the left does not agree with the limit on the right. Okay? Here, I have a surface and a point in the middle. There are an infinite number of directions that I can come from. No, we're not going to try to test all of them. Okay, we have to have a better way to handle these things than that. Okay. But to keep things from being less ambiguous, we'll talk about the definition of a limit. Yeah. This definition does not appreciably change if we go to higher dimensions, but we'll just state it specifically here for two variables so the equations are easier to write down. Okay, I'm going to use a vocabulary word here. A neighborhood is a collection of points that are all infinitely close to the point that we care about. Okay, so we're at the limit as y approaches AB of f of xy is equal to L if for every epsilon greater than 0, there's a delta greater than 0. Such that if xy is in the domain, and the magnitude of xy minus AB, sorry, I should write this in vector form. So basically what we're doing is we have some surface. We'll make like a bumpy surface here that's round, like the example that we had before or something, okay? I have selected this point, we'll select this point over here, all right? And if I picked that point, then the definition says that there has to be some epsilon radius around it, okay? Epsilon can be as small as I like, so this circle could get smaller if necessary. And what has to happen is that when I choose the epsilon value, there has to be a corresponding delta down here in the xy plane. So that here, this would be the point AB, all right? And we choose another circle of radius delta, and as long as xy is within that circle, then I am within the ring here. Does that make sense? Okay. Probably a slightly better version of the picture here, be a little bit more clear, is technically epsilon would be a height. I didn't quite write that right. Okay. And so the point from down below would have to get mapped to a point on the surface that was no more than epsilon difference in height. No, it's probably clear to draw the 2D picture. So if I have a curve in one dimension and this is the point where I care about the limit, the first thing that you do is you specify an epsilon. So this is plus epsilon here and minus epsilon here. So you create this band, all right, of how close you insist that you have to be to the value of the function. Okay. Then you have your point down here that you care about, and what this does is it corresponds to some delta down here. So this would be minus delta plus delta. Okay. And what's happening here is that I'm saying that I have to be this close in height in order to be at least that close height-wise. And then the delta tells me where horizontally I have to choose my points from in order to be at least that close. I'm sorry, say that again.
So, like the points that you choose was like your pink point there, like your X line, and your orange point, your AB. Or is it just the 2 points you chose?
The pink dot that I'm trying to get close to would be AB in the higher dimensional example. Okay, so if I narrow the range for epsilon, then it's necessary for me to tighten up what's going on with delta. Okay, these have to come in order for me to still satisfy that condition. Okay, and the idea is that as the epsilon value vanishes, goes to 0, that the delta value will also have to get closer and closer and closer, right? So you need to be able to continuously move in the domain in both dimensions. All right. And if it's true that the function is always equal to its limit value, then we have the property that we refer to as continuity. There's some visualizations of this in the online notes that are helpful. Okay. Um, one of the things we have to be worried about when we're talking about this in terms of multiple dimensions is if I'm trying to get to a point AB, I can come along many different paths. Okay. Infinitely many. There's no reason that the paths have to be straight. Okay. All kinds of wild stuff can happen. All right. And to deal with this, we have to be a lot more careful about how we think about and approach our limits, especially if we're trying to prove that a limit exists. Okay. There's just a way more complicated set of things to deal with. All right, so let's return to one of the examples we had before. So we want to show this limit does not exist. Okay. Now, before we do this, I want to remind everybody of something. In mathematics, there is a concept known as a counterexample. Okay? A counterexample is sufficient to show that a statement is false. Okay? Now, I want to be a little bit more careful about the words that I'm using here. Okay? A tautology is a statement that is always true. Okay? Now, it can be the case that a statement is true sometimes, right? But not true all of the time. When we're making mathematical statements about things, we want our statements to be tautologies. We want them to always be true. Okay. So when we talk about a theorem in mathematics, all right, the theorem is not a theorem unless it's a tautology. It is always true so long as the appropriate conditions are satisfied. Okay. Or in this case, if we want a limit to be a particular value, we can show that it is not equal to that because we have the condition that says that all of our paths have to result in the same value for the limit. Okay, so if we can find a path or a pair of paths that give differing values, then that is sufficient as a counterexample to show that the limit does not exist because not all possible limits agree. Okay, it is not acceptable on things like the true-false questions on our exam that we just took, for instance, to provide an example where something works and use that as proof that it's a tautology. Does that make sense? Okay. Proving that something's always true is harder, right? That's why the instructions on the exam said explain why it's true or give a reason or an example why it's false. right? That example in this sense would be a counterexample. Okay, so we have to. It's much easier to prove that a limit doesn't exist than that a limit exists and is equal to a particular value. Okay, which is what the rest of the examples that we're going to be working on today are going to be about. Okay, so here we're just looking for a counterexample, and all we need to do is pick a couple of paths that differ in the answer that they give. Okay. So let's choose the path x equals 0. That is, we're traveling along the y-axis. Okay. If we choose the path x equals 0, then we can, you don't have to write it this way, but you can replace 0 here, replace the x here with the 0. Then we get this expression as the one that we're trying to find the limit of. And we can see that this reduces to -1. If we choose the path where y equals 0, okay, so we have found our counterexample. Make sense? All right. So if you're trying to disprove that a limit exists, the best approach is to look at the equation and try to be clever. Okay. And it won't always be the case that choosing x equals 0 and y equals 0 are going to be the paths that give you differing results. It's going to depend on what particular surface it is that you're examining. Okay, for instance, let's take a look at this example. So we have the limit as xy approaches 0, 0 of xy squared divided by x squared plus y to the fourth. Okay, want to see if we can figure out if this exists or not. Okay, so we have a little bit of thinking to do about this one. Okay, for instance, if we were to say pick x equals 0 and y equals 0, is that very helpful in this case? It's not, right? Because all it does is it just zeroes out the numerator, and I'm going to get 0 every time. Okay? So it might be the case that this limit exists, okay, but we need to be a little bit more mindful of how to set this up. So that first trick isn't going to work for us, all right? But maybe we can think of something that'll be a little bit more clever. How about, sorry, I wrote this wrong. The point that we care about is 0, 0, right? And we can, by remembering the point slope formula, imagine that we have a stand-in for a bunch of possible lines, right? Except we know that this line has to pass through the origin, so I don't need B. B is 0. And so I can look at this and see if I get something that is more helpful. Move down here, so we're out of space. Looking at this expression, I can factor x squared out of everything. So I'm going to factor out x squared and simplify. So we're going to be left with mx in the numerator and 1 plus m to the fourth x squared in the denominator here. All right. Now that I've rearranged this expression to be in this form, I can take the limit because there's no danger of me ending up with 0 in the denominator. This is a continuous function of one variable. Okay, everything I know about limits I can still use. Okay, make sense? Because if I plug in 0, I get 0 divided by 1, regardless of what the value of m is. Because m's either 0 or it's not 0. In either case, I get 0 over 1. Okay, so here we get that the limit is 0 for all straight paths through the origin. Okay, now, question, is that enough? It's not, because I don't have to approach the point on a straight line. Okay, so I have to worry about all these curvy paths, and there's no possible way for me to eliminate all of these things by going through them systematically. So we hope that there's a better tool here. And one of the things that we can check, for instance, in this particular case, is if I look at the path x equals y squared, then if I rewrite f by plugging in y squared for x, then we're going to get y squared times y squared over y squared squared plus y to the fourth here. This is going to give me y to the fourth over 2y to the fourth, which is 1/2. That's a constant, so its limit is definitely 1/2, right? And so we get a situation where the limit does not exist.
Why would you not do y equal to x squared? Is it different to the constant? So does it matter?
This is just a matter of looking at the equation and figuring out which thing is going to be the most helpful. I'm trying to get y to the fourth everywhere. So in order to do that, I would have to either the choice if I wanted to do y instead would be the square root of x because that's the same path.
Would you not do like also like y could be equal to x squared since that's also a non-straight path?
Any choice of path is fine. The reason that I chose this particular path is because it's the one that breaks the equation.
Okay.
So this is a matter of you have to look at the equation and figure out algebraically what this thing isn't going to like.
So then like on parabolic curves, like yes, straight is 0, parabolic curve is 0. This is the one that breaks it, and that's where you're trying to.
Yeah. The point of showing you this is that what we don't want to have to do is hunt for counterexamples like this in case where limits don't exist. Okay. We want to have better sets of ideas about what to do, continuity properties, things like that, or to rely perhaps on plots of surfaces in order to help us out here. Say, for instance, in this case, if we were to plot what we have, it was xy squared divided by x squared plus y to the fourth. Okay. And plotting it, we see that there's a huge problem at the origin. Let's see, that has that split sort of behavior in the middle. It'd be easier to see, I guess, if I turned off the XY plane. Okay. Now we can see where the problem is, right? It's mostly 0, except you can find these parabolic paths that send you to different values. So there you can find limits basically everywhere between -1 and between -1/2 and 1/2. It looks like by changing what path you choose. All right. The answer to a lot of these cases is to use the squeeze theorem. If you have a limit that you need to prove and it's one of these harder forms, like this, okay, we're not going to make any progress trying to eliminate all possible paths. There are literally infinitely many of them. Doing that is a waste of time. Okay, so what we need to do is, instead of doing the thing that we would do in Calc 1, which is just check the limit from the left, check the limit from the right, and then make sure that they agree, because when there's only two paths, it's really easy to check all of them. Okay, we instead need to rely on theorems. Okay, one of the theorems that we had from Calculus 1 to deal with troublesome limits was the squeeze theorem, and the other one was continuity properties, right? We have a list of functions that we know are nice under certain conditions, as long as we're not doing things like dividing by zero or taking the square root of negative numbers or whatever, all right? And we rely on that in order to express information about the limit. Here, is this thing continuous at zero or not? We don't know, because we know that we end up dividing by zero, right? We've seen examples of things where we had x squared plus y squared in the denominator, one that worked with sign, one that didn't work with x squared minus y squared. Okay, so here we need to figure out if we can do this or not. Now, for this one, if we were to go to the trouble of testing things like y equals mx and y equals x squared and x equals y squared, we would get zero a bunch of times, okay? Which would lead us to think, okay, maybe this one's going to work, all right? But in order to prove that it's going to work, we need to use a better tool. We also need to appeal to the definition of limits. We're going to let epsilon be greater than zero. We require delta greater than zero such that if the square root of x squared plus y squared is less than delta, then the absolute value of 3x squared y over x squared plus y squared minus 0 is less than epsilon. Okay, so we get this from taking the distance from xy to 0, xy to the 0 vector, right? So it would normally be x minus 0 quantity squared plus y minus 0 quantity squared all under the square root. But that's what we have. Yes, that absolute value is technically redundant because square roots have to be positive, but I'm not going to mess with it. Okay, so now what we want to do is we want to reorganize some information here. Okay, if I examine this expression, everything is positive except for the y. Okay, so what's the only thing that holds on to the absolute value? That makes sense? Okay. And x squared has to be less than or equal to x squared plus y squared. Because x squared plus y squared is a non-negative value, right? And because this is true, it has to be the case that's less than 1, right? Because this is less than 1, this has to be less than this. Multiplying a positive number by 1 makes it smaller. The definition, well, at least an equivalent to the absolute value of y, is the square root of y squared. These are equal, right? This is less than this, which is less than 3 times delta. So we choose we choose delta to be epsilon over 3. And we get to retrace our steps a little bit. We get 3x squared y over x squared minus y squared minus 0 is less than or equal to 3 times x squared plus y squared is less than 3 delta equals 3 times epsilon over 3 is equal to delta, or equal to epsilon. So this less than epsilon, we've satisfied the definition of the limit. Make sense? Okay. So one way is to apply the definition of the limit, which we've done here. Another way is to apply the squeeze theorem. Okay. I know we're out of time. We can play around with that as an example later if need be. I will also say as a final note that the definition of continuity is continuity. Okay. If a function is equal to its limit at a point, it's continuous at that point, and it is continuous on a domain if it satisfies the point-wise continuity definition at every point on that domain. All right? Okay. Take care, and I will see you next time.